a revolutionary construction method that can build entire skyscrapers in a single day without a single crane. Experts call it the future of architecture, and the world is still trying to figure out how it's even possible. Get ready, because what you'll see next feels like magic turned into reality. Let's go!
Number 13. Autonomous construction machines. Bricklaying robots. Construction sites are being taken over by machines that don't need human operators. Specialized robots now handle specific tasks with precision humans can't match. Bricklaying robots can place thousands of bricks per day with perfect alignment, never getting tired or making measurement errors. Concrete pouring robots distribute material evenly across large areas, maintaining consistent thickness. Finishing robots smooth and level concrete surfaces to exact specifications. Window installation robots handle heavy glass panels with millimeter precision. Autonomous construction vehicles build roads by following pre-programmed routes, laying asphalt at consistent speeds and thicknesses. Each robot specializes in one task, but performs that task with relentless efficiency. The advantages are obvious. These machines work around the clock without breaks, dramatically accelerating project timelines. They don't make the mistakes that tired human workers might make at the end of a long shift. Quality control is consistent because robots follow their programming exactly every time. Construction companies save money on labor costs while getting projects finished faster. Safety improves because robots handle the most dangerous tasks. However, this technology raises questions about employment in the construction industry. As robots become more capable and affordable, fewer human workers are needed on job sites. The industry argues that humans move into supervisory and programming roles, but the transition is challenging for workers whose skills become obsolete. Despite these concerns, autonomous construction machines are spreading rapidly because the economic advantages are too significant to ignore.
Number 12. Bridge launching. Moving massive structures through air. Watching a fully assembled bridge slide into place feels like witnessing something impossible. Italian engineer Marco Rosanoli developed this technique that completely changes how bridges get installed. Traditional bridge construction means building everything piece by piece directly over whatever gap needs crossing. That process takes weeks or months and creates massive traffic problems. Bridge launching flips the entire approach. The bridge sections arrive at the construction site already manufactured in factories to exact specifications. Workers assemble these sections on solid ground, next to where the bridge needs to go, not suspended dangerously over open space. Once assembly is complete, a launching nose, basically a metal framework made of girders, gets installed over the span. This framework provides crucial support for what comes next. Specialized machines that weigh several tons lift the entire bridge structure and place it on bearings coated with low-friction materials. These bearings allow the massive bridge to slide smoothly without bending or warping. Then hydraulic jacks push the whole thing sideways, slowly sliding it across the bearings until it reaches the exact position between the support piers. The sight of thousands of tons of steel and concrete floating through air is absolutely mind-blowing. For smaller bridges, the entire structure moves in one go. Larger bridges require incremental launching, where sections get pushed forward while additional segments attach at the back. The coordination required is intense because any miscalculation could damage or destroy the entire bridge. But the speed advantage is enormous. Projects that would normally take weeks get finished in days. Cities appreciate the reduced disruption to traffic and daily life. Construction companies love the improved safety, since workers aren't building suspended over dangerous gaps. I'm going to ask you a simple question. Are you a naturally curious person? If you're watching, I'm pretty sure the answer is yes. This space is made for people like us. To ensure you're always part of this community and receive all our latest discoveries, you just need to do one thing: subscribe to the channel. It's the best way to stay connected with us. Okay, now that you're part of our Legion of the Curious, let's move on to the next item. Number 11. Kinetic architecture. Buildings that move and adapt. Buildings that can transform their shape sound like science fiction, but kinetic architecture makes it real. This construction technique creates structures with moving parts that serve practical purposes while looking absolutely spectacular. The Milwaukee Art Museum features one of the most famous examples, the Burke Brise Soleil. This massive wing-like structure opens and closes like a bird, spreading its wings, providing shade for visitors and protection for the museum during storms. The engineering behind these moving elements is incredibly complex, requiring precise calculations to ensure the mechanisms can handle constant movement without breaking down. But kinetic architecture goes way beyond one impressive building. The One Ocean Pavilion has entire facades that move in coordinated patterns, creating ever-changing visual displays. The Bund Finance Center took it further with facades that open and close different sections of the building depending on how many people need to use the space. The Al Bahar Towers in Abu Dhabi use an umbrella-like system that responds to the sun's position, opening and closing throughout the day to prevent glare and reduce heat gain. The most impressive example might be the Sharifi Ha House, where entire rooms rotate to expand interior space or close off areas as needed. These aren't just gimmicks. The moving elements solve real problems like temperature control, light management, and space optimization. As technology advances, sensors and automation make these systems smarter, allowing buildings to respond automatically to weather conditions and occupancy levels. The construction method requires specialized materials that can withstand constant movement, along with motors and mechanisms built for reliability. Maintenance costs are higher than traditional buildings, but the benefits in energy efficiency and user experience make it worthwhile. Number 10. 3D knitted formwork, fabric becomes structure. Swiss researchers at ETH Zurich created something that sounds completely counterintuitive: building concrete structures using fabric. The technique is called 3D knitted formwork, and it's revolutionizing how complex curved structures get made. Traditional concrete work requires rigid molds that are expensive to build, especially for curved or warped shapes. 3D knitted formwork replaces those rigid molds with fabric. An industrial knitting machine creates a double-layered cloth in the exact dimensions needed for the planned structure. This cloth gets stretched into shape using ropes and a boundary frame, forming the mold. Then, concrete gets sprayed onto the outer layer in a thin but strong coating. Once the concrete dries, the boundary frame and ropes get removed, and the structure stands completely on its own. The Knit Candela Pavilion in Mexico demonstrated just how strong this method can be. The fabric mold weighed only 55 pounds, but the finished structure weighed 5 tons and stood completely freestanding without any support columns. The strength-to-weight ratio is remarkable. Beyond strength, this method allows builders to create steep curves, waves, and complex shapes that would be incredibly difficult or expensive with traditional formwork. The fabric can be shaped in ways rigid molds simply can't match. Construction time is dramatically reduced since there's no need to build and then remove heavy wooden or metal forms. The fabric can be reused multiple times, and the amount of waste generated is minimal. Architects love this technique because it opens up new possibilities for organic, flowing designs that would be impractical with conventional methods.
Number 9. Floating foundations for wind turbines. Renewable energy goes deep. Wind energy faces a geography problem. The best winds blow far from shore over deep ocean waters, where traditional turbine installation is impossible. British and Japanese engineers solved this with floating wind turbine foundations. Traditional offshore turbines stand on bases that extend down to the ocean floor, which only works in relatively shallow water. Floating foundations use a completely different approach borrowed from oil rig technology.
The turbine sits on a semi-submersible or fully submersible platform that floats in the water using buoyancy. The platform doesn't drift randomly. Strong anchor lines tether it to the seabed, keeping it in position while allowing for wave motion. This technology unlocks vast areas of ocean for wind farm development. Deep water locations often have stronger, more consistent winds than shallow areas, meaning better energy production. Countries with limited shallow coastal waters can now develop offshore wind resources. The platforms need to maintain stability despite waves and currents, which requires sophisticated engineering. Different designs exist, including spar-type platforms that hang deep below the surface and tension leg platforms held in place by taut mooring lines. Installation is easier than traditional fixed-bottom turbines, since the floating platforms can be assembled in port and towed to location. No expensive offshore construction crews working from boats and rough seas. Maintenance access is also simplified. As the world pushes toward renewable energy, the available shallow water sites for wind turbines are filling up fast. Floating foundations remove that limitation, potentially opening up enough space for wind energy to scale dramatically.
Number 8. Inflatable concrete. Building with air. Construction sites usually mean heavy machinery, countless workers, and months of labor. But what if you could build an entire structure using nothing more than air and some smart engineering? That's exactly what Italy's Dante Bini figured out with inflatable concrete. The whole thing sounds impossible until you see it in action. Workers start by laying down a canvas shaped like whatever they're building, usually a dome. This canvas gets pumped full of air until it takes the exact shape needed. Once inflated, steel reinforcement bars get arranged over the surface in a grid pattern, held up by the air-filled dome underneath. Then comes the concrete, poured over everything until the entire surface is covered. After the concrete hardens and sets completely, the inflatable part gets deflated and removed. What's left behind is a solid, freestanding structure that's remarkably strong. Emergency response teams love this technique because entire shelters can go up in record time when disasters strike. The labor requirements are minimal compared to traditional concrete buildings, and the best part is reusability. That same inflatable dome can be used over and over for multiple projects. The speed is unmatched, the cost is lower, and the results are surprisingly durable. Whether it's temporary housing after earthquakes or quick military installations, inflatable concrete has proven it can handle the job. The technique has spread across continents, showing up everywhere from disaster zones in Asia to experimental architecture projects in Europe. Some companies have even started using it for permanent structures like warehouses and storage facilities. The structural integrity holds up remarkably well against weather conditions, and the dome shape naturally distributes stress evenly across the entire surface. Engineers have tested these structures against strong winds, heavy snow loads, and even minor seismic activity. The results consistently show that inflatable concrete buildings can match or exceed the durability of traditionally constructed buildings while cutting construction time by more than half.
Number 7. Algae facades, living windows that heat your home. German construction companies figured out how to turn building facades into living, breathing organisms. Solar Leaf and similar companies are installing windows filled with algae that actually work for the building. Picture this: glass panels filled with water, a bit of carbon dioxide, and colonies of algae that grow right there in the facade. These aren't decorative plants. These algae are working overtime, absorbing sunlight and converting it into heat that gets captured and used to warm the building. The heat doesn't just disappear into the air, it gets recycled through the building's heating system. But that's only the beginning. As these algae multiply and grow, they can be harvested and converted into biofuel for clean energy production. The whole facade becomes a power generator. The system gets even smarter when you look at seasonal adaptation. Summer rolls around and the building needs cooling? Let the algae grow thick and dense, blocking more sunlight and heat from entering. Winter arrives and you need warmth? Harvest some of that algae, thin out the colonies, and let more light through while the algae produce heat. It's basically nature's smart curtains, except these curtains are also making fuel and controlling temperature automatically. The visual effect is striking too. These buildings have this vibrant green glow that shifts and changes as the algae grow. From inside, looking through algae-filled windows creates this unique filtered light that changes throughout the day. The BIQ house in Hamburg became the first residential building to use this technology, and the results convinced skeptics. The energy savings are real, the biofuel production works, and the temperature regulation is better than conventional systems. More buildings are adopting this approach because the benefits stack up. Reduced energy costs, renewable fuel production, natural temperature control, and striking aesthetics all in one system.
Number 6. 3D concrete printing. Houses built in hours. Giant 3D printers are constructing entire houses in timeframes that seem impossible. These machines lay down concrete layer by layer, following digital blueprints with perfect precision. The printer moves on a large gantry system that can cover the entire footprint of a house. The concrete comes out of a nozzle in a thick ribbon that hardens quickly. By the time the printer completes one full circuit around the emerging structure, the lower layers have solidified enough to support additional layers on top. The process continues upward until walls reach their designed height. Some printers can complete a small house in 24 hours. Larger homes might take a few days. Compare that to traditional construction that takes months. The concrete used is specially formulated to be printable. It needs to flow through the nozzle but harden rapidly once deposited. The resulting structures are surprisingly strong, with layer adhesion creating solid walls that meet or exceed building codes. Precision is extraordinary because the printer follows digital commands exactly. Every wall is perfectly straight, every corner is precisely square, and every dimension matches the blueprint exactly. The printed patterns create interesting textures that many people find aesthetically appealing. Cost savings are substantial since the printer requires minimal human supervision and material waste is almost zero. Several companies are now offering printed homes at prices significantly below conventional construction. Disaster relief organizations are exploring this technology for rapid housing deployment after earthquakes or hurricanes. Developing nations see potential for addressing housing shortages quickly and affordably. The technology still has limitations. Plumbing, electrical, windows, and roofs need to be added separately, but the core structure goes up faster than any other method.
Number 5. Precast modular construction, buildings assembled like Lego. Swedish, British, and Danish engineers perfected a construction method that turns buildings into giant Lego sets. Precast modular construction means every component gets manufactured in a factory before arriving at the construction site. Walls come pre-built with insulation, wiring, and even outlets installed. Windows arrive in their frames, ready to be clicked into place. Floor sections, roof panels, bathroom pods, and stairways all get produced in controlled factory conditions. Quality is consistent because factory conditions allow for precision manufacturing. When these components reach the construction site, assembly happens incredibly fast. Specialized crews use cranes and equipment to position and connect the modules. Design features built into each component allow them to interlock or connect using specialized fasteners. A complete house can be assembled in hours. Skyscrapers that would normally take years can be finished in weeks. The record-setting Broad Sustainable Building in China constructed a 57-story tower in just 19 days using this method. The speed is mind-blowing, but quality doesn't suffer. These modular buildings are just as durable as traditionally constructed structures and often more consistent since factory manufacturing eliminates the variations that come with on-site construction. Labor requirements drop dramatically because a small crew can assemble what would normally require dozens of workers over months. Waste reduction is another major advantage. Factory construction is efficient, with precise material calculations and minimal leftover scraps. Weather delays become irrelevant since most work happens in factories. The construction site just handles final assembly, which can proceed quickly regardless of weather. This method is revolutionizing how the construction industry thinks about building, turning construction from a craft into a manufacturing process.
Number 4. Transparent aluminum. Windows stronger than concrete. Transparent aluminum sounds like something from science fiction, but this material is real and being used in construction right now. The proper name is aluminum oxonitride, but calling it transparent aluminum captures what makes it special. This material looks like glass, but has strength approaching that of steel. Bullets can't penetrate it. Explosions that would shatter regular glass barely scratch transparent aluminum. The military developed this for vehicle windows and aircraft that need to withstand gunfire. But construction applications are emerging rapidly. Buildings in high-risk locations can use transparent aluminum for windows that provide security without looking like bunkers. Hurricane-prone areas benefit from windows that won't shatter, even when debris impacts them at high speeds. The material can withstand extreme temperature changes without cracking, making it suitable for buildings in climates with dramatic weather swings. Transparency is excellent. Looking through transparent aluminum is like looking through high-quality glass with minimal distortion. The manufacturing process involves pressing aluminum powder with oxygen and nitrogen at extreme temperatures and pressures, creating a crystalline structure that's both transparent and incredibly strong. Cost has been the limiting factor. Transparent aluminum is expensive compared to regular glass. But as manufacturing scales up and techniques improve, prices are dropping. Architects are starting to incorporate it into buildings where security or durability is critical. Bank buildings, government facilities, and high-end residential towers in areas prone to severe weather are early adopters. The material's strength allows for larger window panels with less supporting framework, opening up new design possibilities for glass facades that can withstand anything nature or humans throw at them.
Number 3. Top-down construction, building up and down simultaneously. Construction logic says you start at the bottom and work your way up. American engineers decided that logic needed challenging with top-down construction. This technique completely reverses normal building sequences by constructing above-ground and below-ground levels at the same time. Here's how it works. Workers start building the above-ground floors in the normal upward direction. But simultaneously, excavation begins below ground, creating basement levels one at a time. As the building rises upward into the sky, it also extends downward into the earth. The engineering required to make this work is complex. Each newly excavated basement level provides structural support for everything above it. The basement slabs act as bracing for the retaining walls, bearing loads that would normally require temporary support structures. As excavation goes deeper, each new level takes over the load-bearing duties. Urban construction sites love this method for several reasons. The time savings are huge since work proceeds on multiple levels simultaneously instead of sequentially. Projects finish much faster. Soil movement is also dramatically reduced compared to traditional basement excavation, which means less disruption to surrounding buildings and infrastructure, a critical advantage in dense city centers where adjacent buildings sit close together. The reduced excavation time also means construction noise affects neighbors for shorter periods. There are technical challenges, of course. The coordination between the upward and downward construction sequences requires careful planning and precise execution. The structural calculations must account for loads being transferred through levels that are still under construction. But for high-rise buildings in congested urban areas, the advantages outweigh the complexities.
Number 2. Rammed earth construction, ancient wisdom meets modern needs.
Some of the most effective construction techniques date back thousands of years. Rammed earth construction goes all the way back to the Neolithic era, and it's still being used today because it just works. The process starts simple. Workers create a mold shaped like the wall or structure they want to build. Soil gets poured into this mold in layers. Each layer gets compacted down hard, either by machines or by hand using heavy tampers. This compaction removes all the air pockets between soil particles, transforming loose dirt into something remarkably solid. Layer after layer, the wall grows taller, with each section getting thoroughly compacted before the next layer goes on top. The compression is what gives rammed earth structures their incredible strength and longevity. Once the entire wall reaches its planned height and the soil has settled completely, workers remove the surrounding mold. What emerges looks almost like natural rock formations, but with clean geometric lines. These walls can stand for decades without maintenance. The insulation properties are outstanding. During brutal summer heat, the interior stays refreshingly cool, while in freezing winters, the thick earth walls trap heat inside beautifully. Artists have taken this technique and elevated it to an art form by using different colored soils in layers, creating stunning striped patterns that look almost like geological strata. The environmental benefits are huge, since the main material is literally dirt from the construction site. No transportation costs for materials, no industrial processing, just earth, water, and human effort. Modern rammed earth buildings have proven they can meet building codes while providing energy efficiency that conventional construction struggles to match. The technique has seen a major revival among people looking for sustainable building methods that don't sacrifice quality or durability.
Number 1. Light-emitting concrete, glowing roads, and luminous buildings. German and Hungarian engineers developed something that seems almost magical: concrete that glows in the dark. This isn't some trick with hidden lights. The concrete itself actually emits light. The secret lies in phosphorescent materials mixed directly into the cement. These materials absorb light energy during the day when the sun is out, storing that energy within their molecular structure. When darkness falls, the stored energy gets released slowly as visible light, creating an eerie, beautiful glow. The practical applications are enormous. Roads built with this material would glow softly at night, helping drivers see lane markings and road edges without needing as many streetlights. This could dramatically reduce accidents, especially on rural roads where lighting is minimal. The energy savings are substantial, since the roads essentially light themselves using stored solar energy. Beyond roads, architects have started incorporating light-emitting concrete into building designs. The Sheikh Zayed Mosque in Abu Dhabi uses a similar concept with lights placed behind calligraphy, but imagine if the walls themselves could glow. The aesthetic possibilities are endless, buildings that come alive at night with soft illumination radiating from their very structure. Pathways and sidewalks made with this material could provide subtle lighting for pedestrians without electricity costs. The technology is still being refined to increase brightness and duration of the glow. Current versions can emit light for several hours after sunset, but researchers are working to extend that to all night. The color can be adjusted by using different phosphorescent compounds, allowing for creative lighting schemes. Some experimental installations have created patterns by alternating glowing and non-glowing concrete, producing stunning visual effects after dark.
Still curious? Then don't stop now. The next mystery is already waiting for you. Just click the video on screen. I saved it just for you. See you there, curious one.